The purpose of this video is to demonstrate orthorectification of a single frame aerial photograph using a technique called single photo resection. In single photo resection, we use known points on the ground to resect or reverse engineer the location and orientation of the camera with respect to the ground. This is represented in the figure by the pyramid that's based on the ground with its apex at the focal point of the camera. If we solve for the XYZ location of the camera focal point and the tilt of the photograph with respect to the ground, that's called exterior orientation. And single photo resection is a special case of solving exterior orientation of one photograph using 3 or more ground control points. The upper pyramid in the figure, with its apex at the focal point of the camera and its base being the focal plane, is the interior orientation. In order to solve for interior orientation, we need information that is provided in the camera calibration report. Once the geometry of the vertical photo is solved by using single photo resection, relief displacement can be corrected by using a DEM and projecting each pixel onto a flat surface. So to review, the ingredients we need to make a digital orthophoto are the image itself, the camera calibration report for interior orientation, ground control points for exterior orientation, and a DEM to correct for relief displacement. NAP photography was used by the USGS to create nationwide digital orthophoto quarter quadrangles, or DOQQs, at 1 meter pixel size, or ground sample distance, GSD. You can review the calculations here on your own to see how the scan resolution of 1000 dpi, or 25 microns, was determined. At 1000 dpi, one 9-inch by 9-inch aerial photo should produce a file of approximately 80 megabytes at 8-bit resolution. At this radiometric resolution, brightness values, or gray values, for each pixel range from 0 of pure black to 255 as pure white. The scanned NAP aerial photo that we used in the lab was downloaded from the USGS GloVis site. In that previous exercise, we performed a simple two-dimensional georeferencing in ArcMap to bring that digital image into the GIS. We examined the overlay of that georeferenced image on a USGS topo map and determined that spatial accuracy varied within the digital image based on terrain. We also determined that the pixel size was not 1 meter, as in the original USGS scans, but rather it was 3 meter. This is because the original scans were resampled at a lower resolution to reduce the size of the files for download from GloVis. The downloaded scan was determined to be oriented with north on the left. The USGS logo and black border were added to the digital files for distribution on GloVis. Those were not part of the original scans. Notice that the camera identifier, which is the small white box that has camera and lens serial number, is also on the north edge of the photo, on the left in this orientation. And you can barely see the 8 fiducial marks that are exposed in each photo. There's 1 in each corner and 1 in the middle of each side. The USGS camera calibration reports contain the very precise laboratory measurements for the fiducials as they're located on the camera platen. The fiducials are then exposed in each photo and can be used to correct for any stretching or warping of the film that occurs during processing. Notice that the fiducials are numbered with the data strip on the left side. The data strip was cut off in the scanned image files, but you were instructed that the data strip is the side of the photo opposite the camera identifying box. So in order to orient the scanned image with the data strip on the left to correspond to the camera calibration report, we have to flip the image 180 degrees, as shown here. Now north is on the right. At this point, we can use the calibrated fiducial measurements as control to reference this image scan to the camera coordinate system. This is the most important element of interior orientation. Even the most carefully manufactured lens can have some distortion in the photographic image. Lens distortion is also measured in laboratory calibration, and they give values for it in the calibration report. So corrections for lens distortion can also be applied during this interior orientation process. Now let's see how interior orientation is actually performed. This is the most important photogrammetric operation for frame cameras that is not included in ArcGIS. For this demonstration, I'm using a software package called Summit Evolution, produced by Datum Systems International. Summit is what we refer to as soft copy or digital photogrammetric workstation. To set up a project in Summit, we have to select the type of sensor. There are many options for sensors available in this powerful package. Picking aerial frame camera. A Summit project contains the three components we need to solve the geometry of the photo: the camera file, the image file, and the control file. We're starting with the camera file, and I've already created that and entered the information from the printed USGS report. So you can see the camera information, the fiducial coordinates, the fiducial layout, and there's also a tab to enter the lens distortion. There are a variety of methods for measuring and expressing lens distortion. We're going to use a simple representation of angular distortion. Alright, so that being done, I'm going to save my Summit project file. The next thing we're going to do to add to the Summit project is the scanned image. Summit prefers to work with images in an optimized format, so we're going to begin by converting our TIFF image. Note that I've got the image in the correct orientation. I saved it as in the photo editor, and I also cropped off that USGS label. And now I just check to be sure that the image is correctly listed in the project file. And I'm going to save the project. The last component we need is ground control. Since we don't have access to ground control survey equipment, we previously determined we could use our more accurate, high-resolution digital ortho photos from the PA map program for our control. So here I'm showing the 7 ground control points that I measured that are within the bounds of the NAP photo as it was georeferenced in ArcGIS. Notice the distribution of the points. I'm locating each point on the control image. So I have to zoom in, choose a location, but I also need to make sure that each of those points is going to be identifiable in the lower resolution older NAP image. So I have to examine each one. When I have all my points selected, I can generate control coordinates using calculate geometry. So I open the attribute table. I've done this already. I've used calculate geometry to get eastings and northings. And I've used spatial analysts to extract elevations for each point from the USGS DEM that's also in my ArcMap project. And now I'm exporting this attribute table to a text file because Summit cannot ingest an ESRI shapefile. Now I return to the Summit project to bring in my control file. I have to tell Summit to ignore the first line of the text file because it just contains the column heading labels. So tell it to import at record 2, tell it the delimiter is a comma, and now I need to tell it which field corresponds to the point identifier, the x-coordinate, which is the easting, the y-coordinate, which is the northing, and the z-coordinate, which is the elevation. Okay, I'm going to save my control file. And again, close the window, save my project, and make sure that the control file has been correctly added. Okay, so I've got all the elements I need now: camera, file, image file, and control file. Now I'm ready to perform the interior orientation in Summit. I'm going to measure the fiducial locations in the image in pixel coordinates, and Summit will use the camera calibration information to reference the image to the camera coordinate system. Here's my interior orientation box. The orientation of the photo matches the fiducial numbering in the camera file. The Summit simply drives to each fiducial point, and the operator just has to line up the cursor with the image of the fiducial mark and make a measurement. Now, because the fiducial marks are the same on every photo from the same camera, and they have a very unique and specific shape, Summit and most other soft copy photogrammetry workstations can perform these measurements completely automatically using pattern recognition. So if you were working with tens, hundreds, or thousands of photos, you could save an immense amount of time by using automated interior orientation. As we make the measurements, the interior orientation dialog shows us a statistical fit of the measurements to the control, which should be checked to make sure there are no blunders. See here that I got about 1/4 of a millimeter RMS, which is not great, but it's acceptable considering the rather low quality of the image scan. So again, I'm going to save my project. Now that I have interior orientation, we're going to move on to exterior by measuring our ground control points. I bring in the ground control file and select all the points. Now at this point I have ArcMap open off the side of the screen because I need to be able to identify each point by its appearance in the image. For example, the end of the airport runway. This process takes longer than measuring the fiducials, so I'm only going to demonstrate measuring 2 points in this video so you can see how it's done. Here's my final result, including all 7 points. You see them as small purple crosses in the overview image at top left. At this point, I'm simply going to apply and save my changes. Now I'm finally ready to make the orthophoto. I open the orthophoto tool and I see the image, and I can also turn on the measured control. I have to now add my DEM file, which recall we saved in GIS as a raster IMG. Summit is designed to use a set of elevation points, not a raster image. So I add the IMG and click the Optimize button, which converts the raster to points. And now I'll turn on the footprint of the DEM, and you can see the extent of the DEM, which should always go beyond the edges of the photo that you're going to be processing. And now I simply tell Summit to calculate the ortho, and it will begin resampling the digital image, projecting each pixel into its proper location on a flat surface. Now this will take a minute or so to process, and you'll notice there are some other tabs here that there are a lot of different options you can select in terms of exactly how the image is processed. But the basic underlying mathematical correction of relief displacement is fairly simple and does not really have any options. This is a very automated process. Okay, and now that it's finished, and I save my project, and I can bring up the finished orthophoto has been written to a new TIFF file. I'm just going to bring that up in, I'm going to close the project and bring that orthophoto up in the image viewer in Summit to just take a look at it. Okay, and you can see that there's definitely been some terrain correction, particularly on the right-hand side of the image over Mount Nittany. The image has actually been resampled and pixels have been moved horizontally to account for relief displacement. Okay, at this point we're done with Summit, and we're going to bring the orthophoto image back into our ArcGIS project. So here you see the PA map color digital orthophoto, which was our control layer. And now I'm bringing in the 2D, this is the NAP image that we georeferenced in Lesson 3, and we know that there is relief displacement. And now I just brought in the ortho rectified image, and I'm using the swipe tool in ArcGIS to show you how the ortho image overlays the PA map control surface. And you can see that we've definitely improved the quality of the georeferencing at this point. Our roads are lining up nicely, all our features are lining up nicely regardless of the hilliness or flatness of the terrain. And you can also just compare the orthophoto to your 2D georeferenced image, and again it's clear that there have been some changes. So that's the end of this demo and the end of the Lesson 4 lab. In Lesson 5, you're going to use more limited orthorectification capability that is within ArcMap with a high-resolution satellite image from Digital Globe. I made this demo because it's a lot harder to demonstrate with ArcMap what's actually going on behind the scenes. In ArcMap, orthorectification is simply one button push. But now hopefully you have a better idea of how orthorectification actually works and how the control, the relief, the DEM, and the sensor sensor geometry, sensor calibration information all goes into making an orthophoto.